Hi guys, welcome to my YouTube channel, and in this video we are going to look at bonding in organic molecules. It's a continuation of organic chemistry IGCSE A levels. So we are going to start with one type of bond which is called sigma bond. A sigma bond is basically a single bond between a carbon and a carbon molecule. So there are pair of electrons in the bond that are found in this region in space. Normally the lobe, they are between the nuclei of the two carbon atoms that are sharing the electrons. So there is an electrostatic attraction between the negatively charged electrons and the two positively charged nuclei bonding each other. So for example, here in ethane the carbon has 4 bonds, 3 hydrogen bonds and one bond with carbon. So therefore they form a tetrahedral arrangement with a bond angle of 109.5 degrees. Then for pi bond, they are simply double bond. That is the double bond between a carbon and a carbon molecule. For example, in ethene, which is an alkene. So the carbon atoms that are involved in the bond or in this double bond, they are sp2 hybridized, and each of the carbon atom with one spare outer electrons in the 2p orbital, and when these 2p orbital overlap, then they form a pi bond, or they form a double bond. So this is illustrated in this diagram where we have 2p orbitals above and 2p orbitals below the plane, and the carbon atoms in this arrangement they are said to have a planar arrangement. For example, in this ethene molecule is a planar molecule. So carbon atoms, they are bonded and they have electrons overlapping in the p orbital, one above, so forming a pi bond. The pi bond has a bond angle of 120 degrees Celsius. So there are also other molecules that has 3 bonds, for example, alkynes. So these ones, they have 3 carbon-carbon bonds. So the orbitals here, or the carbon atoms, p orbitals, they are sp2 hybridized, and that leaves 2 electrons in different p atomic orbitals bonding in the carbon atoms, and when those 2 p orbitals overlap, they form 2 pi bond containing 2 electrons, and therefore 3 bonds are formed, the sigma bond plus the 2 pi bonds that are formed earlier. So those questions, you're going to handle them later on. Then let's look at isomerism. Isomerism is where a molecule has same molecular formula but different structural formula depending on arrangement of elements in space, or depending on arrangement of atoms in space. So for example, in propene, we have 3 carbon atoms and we also have 3 hydrogen atoms. But propene can be arranged in different ways. The 3 carbon atoms and 6 hydrogen atoms can be arranged in a chain, or even they can form a cyclic molecule. For example, cyclopropene that is shown in this diagram. So cyclopropene is an example of a cyclic structure, which is a structural isomer. So there are 3 types of structural isomerism, which is positional isomerism, functional group isomerism, and also chain isomerism. Position isomerism, this one, the position of an isomer, or it's the location of the functional group that varies in each type of the isomer. For example, these ones that are displayed here, we have 1,2 dibromopropane, and we also have 1,3 dibromopropane. These 2 molecules are isomers just because they have what? They have bromine molecules that are arranged in different position. One at position 1, position 2, and the other one at position 1 and position 3. Functional group isomerism. In this type of isomerism, the functional group are different. Different functional group are present. For example, in this diagram here, we have propan 1-ol, where the functional group is OH, and in this other one, we have the methoxyethane, and these two are isomers with different functional group with different chemical properties. Then we have stereoisomerism, and stereoisomers are compounds whose molecules have the same atoms bonded to each other, but then they have different arrangement of atoms in space. So they are of two types. We have geometrical isomers, and then we also have optical isomer. For geometrical isomer, we have cis and trans isomerism. For example, this one that is displayed here, when the two functional group are on the same side, then we call them cis. Cis means same size, while trans means they are on opposite side. So the position, there is no free rotation here because we have a double carbon bond, and therefore it results in different types of isomerism. So for example, we have cis 1,2 dibromoethane and ethene, and then you have trans 1,2 dibromoethene, depending on the position of bromine groups. So we can also have different ones, like those ones A, B, A, so they can be, if you have two groups that are similar on the same side, cis, two groups that are similar on different on the same side, on different sides, they are called trans isomerism. So we can have also isomerism being shown in such diagrams, shown in wedge and a dash diagram. So for example, the first one here we have cis3 methyl cyclopentanol. It is called cis because we have the hydrogen, the OH group and the methyl group there facing the same direction, but we have both of them are wedge. In the other one, trans 3 methyl cyclopentanol, one is wedge and one is dash, therefore they are different. They are facing different sides, that's why they are called trans 3 methyl cyclopentanol. Another example is down there. We have COOH group, wedge, opposite side, and then you have a dash and a wedge on the other side. So in the cis isomer, the two carboxylic acid groups are either pointing above or below the ring of the 4 carbon atoms. So but in the trans, the carboxylic acid group points above the ring. The other type of isomerism is optical isomerism. And in this one, so if a molecule has a carbon atom that is bonded to 4 different groups of atoms, then it can form 2 optical isomers. And therefore we can describe them as an asymmetric carbon. So because there is no plane of symmetry in this molecule, and if you have 2 different such isomers, they are called enantiomers, and they are normally mirror images of each other. So the carbon atom with 4 different groups that are arranged attached to it. For example, if you have a carbon with CH3, then with the H, then with the CO2H, and then with the OH group, then all those groups are different, and therefore it becomes the chiral center of those groups. So optical isomer, they normally differ on the effect of on polarized light. So normal light, we say it is unpolarized, and therefore it can be thought of fluctuating or simply changing electric and magnetic field that's vibrating at right angles to each other in every possible direction. But if you pass unpolarized light through a polarizer, then you will resort, or you will have polarized light. That polarized light will only vibrate in only one plane. So if you have a pair of optical isomers, then they will rotate on the plane of a polarized light in opposite direction. So one will rotate maybe clockwise and the other one will rotate anti-clockwise. So if you have organic molecules that contain more than one asymmetric carbon, then that means they have more than one chiral center. So there are two asymmetric carbon atoms, then each of its chiral center will rotate the plane of polarized light. So in this case, there will be 4 possible optical isomers. So if you have a well straight and also a branched chain molecule, substituted cyclic molecules, they can also have chiral center in their ring structure. For example, this one that is shown here. So to decide where the chiral center we have, then we have to find the carbon atoms that is bonded to 4 different other groups. So in this example that is given there, we have it's a cyclohexane, but then we have normally it is bonded, the carbon is bonded to hydrogen atoms, but they are not shown because this is a skeletal structure. But here we have the carbon, it's bonded to carbon bonded to OH group, it's bonded to different groups. That means it has OH group, it has an hydrogen, it has another either group that's a wrong group, and then it is bonded to this other group that has amine. So in this cyclohexane, all the carbon atoms are bonded to 2 hydrogen atoms, so there is no chiral center. But when you start substituting other groups, maybe the OH group, the amine group, the bromide group, or even the chloride group to that carbon, there is possibility of getting a symmetric carbon. That is a carbon that is bonded to 4 other groups. So in this cyclic carbon that is shown here, we have OH group and also we have an amine group. So if we start with this carbon that is bonded to the OH group, you also find that this carbon is also bonded to a hydrogen group that is not shown because of the structural structure. Then there are other 2 groups that are bonded to it, making it have 4 single bonds, and therefore it is a chiral center. So if you start traveling that ring in a clockwise direction, then what will happen when you move in a clockwise direction? So you will find that you will have 4 carbon atoms, that is 1, 2, 3 and 4 carbon atoms that have hydrogen group, that is CH2 group. And then you will come to this carbon that is bonded to amines, CNH2. It has also a H, so it's CH and then NH2. Then if you travel in the anti-clockwise direction, then you will also get you'll get this carbon that is then with it has a H, CH, then it's bonded to an amide group, CHNH2, and then it is bonded to 4 other carbon that have H2 each. So therefore we have an H atom, we have an OH group, we have a CH2, 4 CHNH2, and then we have another CHNH2, CH2, 4. So if you rotate the other side, you will still get a mirror image of that carbon. So those are the stereoisomers and the optical isomers. Then for chain isomerism, chain isomers, they normally differ in the structure of the carbon atoms or carbon skeleton. For example, you have butane. It can be arranged as a chain, that is CH3, CH2, 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 CH3, or you can make a methyl group become a branch, and therefore you have methyl propane, which is CH3, CH, CH3 joined to a CH3. So the next slide is about questions that are about the naming of the types of bonds, the types of isomerism, and also naming them, and we are going to cover them in the next video as organic chemistry questions. See you. Thank you for watching.